Um, Thank you very much. So next up we have Mark Croom from New Mexico State telling us about unveiling the baryon cycle in a sample of edge-on galaxies. So I'll get my thing up. You can go ahead and start. I'll change my background.
Okay, so is it coming through? You hearing me?
Yep.
Okay.
I don't see it. I don't see anything yet.
Oh, you don't?
No, you haven't shared your screen maybe, or?
But probably not. Okay.
There you go.
Okay. All right, good. So let me start by talking about galaxy evolution. Actually, I'm going to talk to more than just one program that's underway at APO. Both deal with galaxy evolution, studying that, and deal with the baryon cycle. Let me also mention my fellow classmates, observers, Bryson, everybody's met, and Farhan Hassan, both from NMSU. And I am, in spite of this, a grad student at NMSU. So with that, let me get into it. Thanks to Jessica, we have already covered a lot of the material of the upfront background. But as I mentioned, I wanted to talk about two different programs, one we call COS Colors and one, a newer one we call Edge-On. We'll discuss how these, both these programs relate to baryonic flow in and out of the CGM, which is illustrated here. The CGM is the intermediary between ISM and IGM, and the baryon cycle crosses through that. So up left is the ISM. And, you know, everybody's taught this in Intro Astro, where baryons condense and create stars, and depending on the mass of the stars, so what, when, and if material is ejected back out. In the bottom right section, you see the outflows going all the way back out to maybe the IGM, or get looped around through some recycling, staying within the CGM, and then some inflows. So how do you know about the cycle? How do you understand it? You know, everything coming in and out through the CGM is difficult to visually, you know, to pick up from an emission standpoint, although things are moving in that direction, but I don't think we're quite there yet. So we have to use other methods, such as using distant quasars to probe this, quote, invisible region that's in the CGM. Emissions are going to be something ELTs maybe can deal with, sounds like, in the future, but right now we're limited to using quasar sight lines and looking for absorption features to see what's going on in the CGM. The material that comes through the CGM, of course, is at the location of the host galaxy that you're interested in, the CGM that's surrounding you. So if you need to know where the host galaxy is in terms of its redshift, so you can match absorption features that happen all along the way, since the, you know, light leaving the quasar, if it's UV bright, you know, get absorbed all the way along the path. But the absorptions that happen in the realm, in the region of the galaxy of interest, is identified by picking the right wavelengths based on the redshift of the galaxy. And it shows a space-based asset, but it depends on the wavelength, like was discussed earlier when Jessica was talking. Depends on the wavelength and redshift as to whether you can access things with ground-based assets or not. So by using this method, looking at the quasar sight lines, you're able to understand a little bit more about the CGM surrounding your host galaxy. The typical species that are used are Mag2 and carbon-4 and oxygen-6, with the rest wavelengths shown in the table. But they represent low ionization, intermediate ionization, and higher ionization for different relative temperatures typical for those species. And the bottom graphic shows, I don't know if you can tell what's going on here, but the quasar sight line is off here on the left, and depending on the CGM layout, you'll get a spectra that could be quite different. You know, all these little clouds would, if they're infalling, then you would expect to see the spectrum shown at the bottom surrounding the systemic velocity of the system on either side. Whereas if you're collecting information on one side and it's rotating, then you expect to see the spectrum over here. So understanding better the CGM itself is a program that's underway that's nearing completion from an APO standpoint, but it's called Cost Colors. And this was, it has a PI of Ben Oppenheimer up at CU. The role is to try to figure out how the baryon cycle fits into regulating star mass and color evolution. And on the right is the color and stellar mass plot showing the red sequence and green valley and blue cloud, and to get an idea of how and why when galaxies evolve, over cosmic noon, going in towards more and more rotationally supported. So there's a program put together, 50 plus galaxies about Z of 0.35 or closer, and distributed across this state space, if you will, between color and stellar mass to try to map that out. Part of the study requires getting UV spectra, and doing that requires knowing precise redshifts, and that's where APO comes in. It's more of a support function, but what we have is using DIS to pick up the spectra to refine the redshifts of these galaxies that are between 18 and 23rd magnitude in the R band. And I just pulled an example. It's at the top, you can see the small little emissions. This is the straight segment. It's on a 200 angstrom segment from DIS. And it's one of the galaxies where we've identified the H alpha emission and a couple of surrounding N2 regions and recompute the redshift. And this is one of the worst, actually, but the photometric redshift that came from just photometric methods is off by quite a bit. And when you're trying to put together a program to go forward to Hubble to get the spectra, I pulled this from a recent effort that I've just been involved with. Not even really sure if these are the same gratings we would be using for this particular program, but if it were, the error that we're seeing, for example, for Lyman alpha would represent about 76 angstrom. So that would be your uncertainty if you use the wrong redshift for this. And you can see you would probably certainly pick the wrong grading, certainly the wrong slant or center wavelength potentially. And especially when you have to worry about these small little black spots, which are gain sags where you don't get much of signal, or actually don't get any signal, it seems like, or gaps in the two different segments. So you want to know precisely what the redshift is in order to then be able to do the studies of looking at the various base metallicity parts of the CGM. So of this program, I had 50 odd. There's 4 that remain to do that we have to get data on with this. And of course, we still have to get selected for Hubble work to move that forward. And I also have to finish my homework and give a data review before we say that we're done with those. All right, so how can you also look at the interaction between a galaxy and its CGM? So understanding the CGM is one thing, then tying it back to how the galaxy and it interact is the other piece. That's another program and others that you've heard today. So looking at star formation, the fuel supply coming in, the inflows, the idea is there's accretion happening around the disk, bringing material into the galaxy itself, raw material, spins the angular momentum build up from that interaction with the accreting gas. Is recent studies show that's probably the case, which makes sense. How do they interact? How do these two things, how does the fuel supply and the kinematics interact between the CGM and the galaxy? And one approach is to get the galaxy kinematics measured using rotation curves and look for spatially resolved star formation rates and metallicities across this. And then of course measure the CGM using whatever methods. That's showing a quasar background sightline being used to do that, and then correlate them. So has this been done? And you know, what species would you look for in the CGM? And it actually has been done for magnesium-2, as was mentioned earlier by Jessica. This is an example shown with work done by my advisor, Chris Churchill, where on the left you see the quasar. This is where the sight line will be, you know, that is the sight line, and it's at a certain position relative to the candidate galaxy. And so you look for at the wavelength of this galaxy, I mean, at the redshift of this galaxy, the wavelengths for this absorption from mag2, and you see that there is a mag2 absorption feature at the right speed relative to the systemic that matches with the rotation curve generated from the long slit spectroscopy of this galaxy. So we say that and there was a study of 50 some odd galaxies that showed this to be the case. What about oxygen 6? This is more energetic ion, and it's not coupled. You can see the rotation curves of several galaxies overlaid together, normalized. And if the O6 were behaving tied to the galaxy, you'd expect things to look like this, where this is a dispersion of the galaxy, of the O6 itself versus distance out from the galaxies. And if everything were lined up, you'd see the peaks of all these lined up with the peak of the galaxy itself, rotation speed. But they're not lined up, and some are even going the opposite way. So O6 seems to be too energetic. It's not coupled to the galaxy. What about carbon-4? Well, that's not very widely studied. Vorloy did some work and found that there are some systems, but he used dwarf galaxies in the study. Joe Burchett, who's my deputy advisor, he found a case, but it was serendipitously found. So basically, it has not been widely studied. So we proposed to study across this energy range between mag2 that is co-rotating with galaxies, and O6, which is predicted to not rotate, and look at various ions across this energy spectrum to see how it behaves. And we were fortunate to get recently awarded time on Hubble on cycle 29 coming up. So we have several dozen galaxies that are edge on, pulled from Dimitri's catalog of 2014. By the way, he's given the next talk. 8 of which are using Hubble, that we have sight lines next to. We selected targets that have sight lines in the major axis, so pointed in the long axis of the galaxy. This showing this middle plot shows the galaxy in edge on view, and then where the quasar sight lines would be. So we'll be able to use APO to do rotation curve data and other mappings, and Hubble to be able to explore the CGM, and then fold that into some hydrodynamic sims. So here's one of the results from APO. We've already started this work. And on right is the image of UGC 9014 taken with Sloan. And at the bottom left is the raw spectrum from DIS on the red channel. So you can see the H alpha line, the surrounding nitrogen, nitrogen lines. And everybody knows that red side goes to the left in DIS. So the sulfur lines are over here. But this was extracted, a rotation curve showing following the H alpha line. So we're developing tools to get this done. All right, so cost colors to close up here. Most of the targets have been done. We have a few that still remain. And again, I have to give a presentation on where we stand with the findings so far. The edges, we're using our good fortune here to get information from the CGM with Hubble over the next, whenever we can schedule this cycle this year, and continuing on getting information about the specific star formation rates and metallicities and the FMR from APO using the ground-based element of that. So with that, I think I'm about out of time. Let me thank APO and the staff, and those guys have been really great, keeping us on track, making sure we understand what we're doing. And especially true for newbies like me.
All right, thanks, Mark. Um, any might have time for one very quick question if someone wants to ask it, not in the Slack channel. Otherwise, you can ask in the Slack channel and we can move on if no one has a burning question they want to ask in person. All right. Well, thanks again, Mark. And yeah, it looks excellent. I mean, that's really great that you can complement HST with APO. I think that is awesome. All right, so let's see here. Let me go back to my other background. And we'll move on to the next speaker. So, and we get some more work on thin galaxies. So this one is Dmitry Bezyaev from Apache Point, who's going to talk about super thin galaxies from APO observations. So take it away, Dmitry. I'll switch back to my